time I've said that in here. But yeah, that's the magnitude of r prime of t, delta t. So if you want to get the net arc length, you take the sum I equals 1 to n of the magnitude of r prime. And to be more specific, I really should say which t. If we're talking about this one, it's like ti star. It's that sample point somewhere in between ti and tj, whatever. Ti star, delta t. Oh, and I really should do what? I should take the limit as n goes to infinity of that thing. What is that? So add up the length of each little, what do we get? Well, if you look at the setup, that's exactly the integral from a to b, by the definition of the Riemann integral, of the length, the magnitude of r prime of t, dt. This is the total arc length of the curve that I gave you. So to get arc length, we just integrate the magnitude of the velocity over the appropriate time domain, and there you have it. And so we can forget about this awfulness. It was, and I will answer this question for you guys. I would not ask you this on the test. Okay, so that much I will give that much away. I have a strong suspicion that there's a slightly more careful version of this in Salas and Hilly. He has really nice discussions of multivariate integrals that are not in my notes, by the way, when we get a little bit further in the course. Now, this is the total arc length. We can also talk about the arc length function. What's the difference between the total arc length and the arc length function? So the arc length function, you have a curve, right? You pick a base point. I usually think of it as a starting point, say t naught. And then the arc length function is based on some starting point, and then you go, okay, what's the length of the curve out to parameter t, say? So this is what we would call s of t, based at t naught. So s of t, by definition, is the integral from t naught to t of the length of, let's say, dr dt, dt. That's the arc length function. Any questions? There are some nice heuristics for remembering this stuff, right? I mean, the way I like to think about this, honestly, guys, I mean, I don't usually think about this picture. What I honestly usually think about is something like this. I think about like a little segment maybe, and then I just think about breaking it up into something like. Is there a question? Oh, no? Okay. So if I have, I'm trying to think of a good picture here. Well, forget the picture. Basically, it's just this. If you have ds squared, it's coming from dx squared plus dy squared plus dz squared in 3 dimensions. And so to rewrite that in terms of a parameter, I just simply multiply and divide by dt squared. So what that gives me is ds squared is equal to dx dt squared plus dy dt squared plus dz dt squared, and then all of that dt squared. In some sense, I just multiplied by 1. Of course, this is just formal nonsense, but on the other hand, it's kind of awesome because there you go, right? This is other notation that's sometimes handy when you get tired of writing what I was writing. Yeah, that's the dot, x dot is the x velocity, y dot is the y velocity, z dot, z velocity. This notation is from Newton. It's, well, you don't see it too much, but there it is. But, you know, to me, it's not, obviously that's not a derivation of the formula, but it is a nice way to remember it if you forget. All right, so what are the properties of the arc length function? What are the properties of the arc length function? Can you tell me? It's positive. I think that's, yeah, that's pretty safe to say. We're integrating, well, I guess it depends on my picture, right? If we allow t to go, if we did allow it to go before time 0, then I'm not so sure. But assuming that time 0 is the starting point and we don't allow times before, totally on board with you, it's positive. Because we're integrating something that's positive, right? What happens if you differentiate the arc length function? d dt of s of t, what is that? d dt, the integral from t naught to t, magnitude, dr dt, I can't use, curses, the old using t in two ways problem. Let's use a tau as to not be math heretics. I have to use a different dummy variable of integration since t has a different meaning. It's the upper time, it's the time that we're differentiating with respect to. What do we do? No, I'm differentiating with respect to time. But that, I have to, the integral over the arc length is done over some other variable. I could use a u or something, but I don't. Remember, fundamental theorem of calculus, part 1, says what? This is what? Magnitude of dr dt at time t. So there you have it. The magnitude of the velocity is ds dt. That's good, right? The magnitude of the velocity is the time rate change, infinitesimal time rate change of the arc length function. You may have been told this before, but maybe you haven't seen it proved before. There it is, proof. Exciting. What does this say then? If the velocity of the curve is never 0, what does it say about the arc length function? It's always changing. Very good. If dr dt is not equal to 0 for all t greater than or equal to t naught, that implies that ds dt is greater than 0. Strictly greater than 0. In other words, the arc length function is strictly increasing. What do you know about strictly increasing functions? They're what? They're what? I just didn't hear you. They're infinite. That's true. Well, maybe not. I mean, you could have one of these deals. It could always increase towards an asymptote but never get there. That can happen to us. They're non-decreasing is exactly the answer I'd expected from you. You're like, my brother was working on this math camp with some high school students, and they're team 4, and they're asked to choose a name. What name do they choose? We're team 3. Yes, that resonated. That spoke to your heart, didn't it? It did. I can tell. Yes, that's good. Now that is also true, but not what I'm looking for. I mean, he was on the right track. If a function is strictly increasing, that means it's 1-to-1. It would pass the horizontal line test. A horizontal line would never hit it twice. In other words, the function's invertible. So this would imply that S is strictly increasing, which would imply that S is invertible. That's important because what that means is that you can take the time parameter for such a curve and you can replace it with the arc length as its own parameter. If I have time, I'll show you an example. I do. Woo. So suppose you have R of t is, I'll keep it simple, cosine t, sine t. Since we only have 3 minutes, I'll do a 2-dimensional example. It will suffice to serve my point. What's the speed of this thing? R prime of t is what? Minus sine t cosine t. So that tells me the speed is what? Oh, curses. Speed is 1. Fine. So this is ds dt, so you can see from this that it's already arc length parameterized. T is arc length here. They're one and the same. Dang it. All right, I'll show you an actual example tomorrow. I'm sorry. If I'd done a helix, then we would have had some.